We are going to explore backpropagation today, a key process that allows neural networks to learn and improve. But before I talk about backpropagation, let us have a brief understanding of some associated terms. A neural network is essentially made up of several layers of neurons that are connected by weights. These neurons are also referred to as nodes. The layers are then classified further. The structure has an input layer at the start. The two layers in the middle are the hidden layers, and the layer at the end is the output layer. All the neurons in these layers are linked to one another across the different layers, meaning every neuron in one layer is connected to every neuron in the next layer. The input data moves through the layers in a process called as forward propagation. As it passes through the layers, the weights, biases, and activation functions alter the data until an output is generated. Let us break down this further. First, what do we mean by the weights in the context of a neural network? The weights determine the strength of the connections between the neurons. Next, we apply the activation function, which is used on the weighted sum of the inputs at each neuron. This introduces nonlinearity into the network, enabling it to model more complex relationships. The activation functions is key to this process. Common examples of activation functions include sigmoid and ReLU and some others. Lastly, let us talk about biases. Biases are extra parameter that adjust the activation function, shifting it left or right, which enhances the model's adaptability. Imagine a single training example with its corresponding input data. This data moves through the network and each neuron computes a weighted sum of the input, which is then processed by its activation function. The final output is the network's result. Now, the question is, where does backpropagation fit in? The initial output might not be accurate. So the network needs to learn from its error and fine tune its weights for better performance. Backpropagation is the algorithm that trains neural networks by correcting errors, following the principle of error correction. After forward propagation, the error is calculated by finding the difference between the network's output and the expected output. This error is referred to as the loss function. The error is then propagated backward through the network, giving each neuron a sense of how much it contributed to the overall error. By applying these techniques, backpropagation modifies the weights and biases of the network to reduce the error. The goal is to enhance network's output accuracy in future forward passes. This is an optimization process commonly utilizing a method called gradient descent. Now, as for gradient descent, it would fill an entire video in its own, but in short, it's an algorithm designed to identify the best weights and biases that minimizes the loss function. It adjusts the weights and biases step by step in a way that most quickly reduces the error following the steepest descent path. Backpropagation is commonly used in various neural networks today. For instance, in a speech recognition system, we input a spoken word and the system outputs the written form of that word. If during training the spoken input does not align with the expected written output, the backpropagation can assist in correcting the error. We would calculate how the loss function changes with the respect of the network's weights and biases and adjust those weights and biases accordingly. This process would be repeated through several cycles of forward and back propagation, fine tuning the weights and biases until the network converges. That is a point where the written output accurately reflects the spoken input. Let us discuss one more aspect of backpropagation: the difference between static and recurrent backpropagation network. We'll start with static. Static backpropagation is used in feed-forward neural networks, where data flows in one direction from input layer to the output layer. Examples of this include optical character recognition, that is OCR, where the goal is to identify and classify letters and numbers in an image, and also spam detection, where a neural network learns from features like email content and the sender's address to classify emails as spam or not a spam. Backpropagation can also be applied to recurrent neural networks. These networks have loops, and the backpropagation process is more complicated due to their recursive nature. For example, RNNs, that is recurrent neural networks, are commonly used in sentiment analysis, such as evaluating the sentiment of a customer product review. Another common application is time series forecasting, like predicting stock prices or weather patterns. Overall, backpropagation plays a crucial role in the learning process of neural network. It identifies the error by moving backward from the output layer to the input layer, adjusting the weights along the way to reduce future errors.